All right, so last time we were in the process of writing this linked list, we wrote the interface. That's just kind of a gross bunch of code. Once we finish with this, I'll walk people through my documentation standards and just the kinds of documentation you will want to have for projects, not only for this course, but just moving forward, since starting about here at the 212-300 level in the curriculum, you're going to start shifting focus into preparing yourself for internships, jobs. So every class that you take, especially something from me, I want there to be some outcome. And in this class, there will be many outcomes where you can add code to a repository so that you can show prospective employers what you've done, what you coded, what you can do, your understanding of it. And that is, of course, much better if it is well documented as well. So everything that we do in this class, everything that we write in class, every lab that is assigned that's related to one of these data structures, my recommendation is store it somewhere on the cloud. We can talk about how to set up a GitHub account so that you should all have some kind of GitHub repository as you move toward getting internships or jobs in the field. It'll be great to just be able to share that GitHub with prospective employers so they know what you've done. In the actual linked list class, so we have the interface, we have the node class that's all finished up. We just now need to make sure that we finish up the linked list. We wrote what's probably going to end up being a temporary constructor for the moment. We'll see if there end up being any issues with this. In the future, we wrote an add, but we need to write another add. And to really get started with many of these other methods that we're going to write, we need to write a helper method. Have we seen helper methods before or know the concept of a helper method in a class? So we see that this add method is public, which means that the end user, obviously you're not going to be the person who uses this linked list necessarily. Your goal is to write some structure that somebody else can use. You could publish this linked list code and then somebody could import it, just like you import a scanner and then just use it. You can write a linked list class like this and publish it, and then someone can just go import it. And to do this, any method that is public is something that they can call, which makes sense for a method like add, right? An end user who wants to use a linked list should be able to add to that linked list. There might be some methods that we want to call that we don't want the end user to be able to call because it's either a helper function for one of our functions or it's just something that's outside the purview of what the end user needs to know in order to use the application. So the one that we're going to write here is going to be the one that finds the node before the current node. Since we're not using a doubly linked list yet, there's no .prev or .previous, whatever we want to do to go backwards. So we need to write the associated logic that's going to get us the previous node so that when we try to add a node in the middle of the linked list, we can connect it up with the previous and next. We're going to be inserting it in between two existing nodes. It would be much easier if we had a doubly linked list. Does anyone know or can think off the top of your head, why would you prefer to implement or use a singly linked list over a doubly linked list? It's probably going to be more work to write the singly linked list because we have to write these helper methods that do things like find. We would normally just be able to say .prev and get the last, but now we need to write some associated logic that's going to get us to that point from the beginning rather than from the current node that we're doing. It's a great idea though. Why else would we care? It should operate at about the same speed, but when we start talking about efficiency later on this quarter, one of the things that we're going to note that there are two kinds of efficiency. There's the length of time that it takes for things to run, and there's also the amount of space that it's going to take up in memory. We have a finite amount of memory in our machines. So oftentimes we end up thinking about, and we're not necessarily running this code on my machine. We don't know whose machine it's going to be running on. So the more efficient we can make it, the more machines that it will be able to run on, and or the more larger lists we can make before we run out of memory on any given machine. So if you think of the actual storage structure for a singly linked list, we have a value and an X pointer. If this is a singly linked list and it looks like this, if we are doing a doubly linked list, each node is going to look a little bit different. We're going to have a previous pointer and a next pointer and the value here in the middle. So we can see that each node of a doubly linked list is going to be larger than that of a singly linked list. And you're imagining now that you want to store 1,000 values in here. Maybe this is a voter registration system and we need to make sure that every registered voter in the state of Washington has a node associated with them in a list somewhere. There are a lot of drivers in the state of Washington. This could end up taking a lot of space. So shaving off one of these pointers from each node is going to scale with the number of nodes that we have in our list. So it ends up being a memory efficiency thing to implement this instead of this. It's worth knowing both, but there are times when we're going to prefer one or the other. This makes our life a little bit easier as a programmer, but the computer hates it because it takes up more storage. This makes our lives a little bit harder, but the computer says, I can now store more nodes with the same amount of space. We'll talk about how to formalize this idea a little bit later, but I just wanted to motivate the necessity of thinking about a singly linked list versus a double linked list before we get too deep into this. All right, so we're going to write this helper function that is going to be a private method rather than being a public method. And what that means is it cannot be called outside of this class. But if we're just finding the node before the current node, is that something that needs to be done outside of this class? Is there any reason that the end user would need to reference the previous node from the current node? Not by the functionality that we specify in our interface, right? So we are just going to write this helper function. So we're going to call this, it's going to be private. If we're trying to find the node before the current node, what should the return value be? A node. Since we're generic, we need to make sure that we specify the type. It's going to be the generic type. We're going to call this find node before. And it's going to take the index into the linked list that we want to find the node. We want to return the node before the index of the node that is the parameter. So we're going to pass it an index. So we need to start basically at the beginning of the list, and we need to start iterating up until we reach the index that is passed in -1. Or really I -2, right? Since we're zero index. So we're going to start out some counting variable at 0. We're going to specify we need some temporary node that we're going to store. I'm just going to call this cur. We're going to set that equal to the head, whatever the head happens to be. It can either be null if it's an empty list, or it can be an actual value ahead of time. So these are the preliminaries. Now we need to enter a loop. So we want to say while the value of our counting variable is less than the index before the index that we care about. So what value should I put here if we're trying to get to the node before the query index?
Index -1.
Yes. How do we move to the next node from the current node? Yeah. Is there any reason why we would think this might be null or empty or something of the sort? Maybe we should throw some kind of exception The issue with this is we don't really want to throw an exception that the user sees here because it's not embedded in our list interface. If the user looks at this interface and sees what could be thrown here, and they get an exception that didn't come from one of these things, that would not be great. So we're going to leave it and assume that it works for now. This is why it is worth testing these things. We'll talk a little bit, especially if you're in 212 this quarter, we'll talk a lot about testing. But you'd want to make sure that this is very well tested so that it doesn't communicate something to the user that they're not expecting. All right, outside of this, what else do we need to do? There's one very important thing we have not done. Two important things. That's the first one. We want to very much return cur at the end.
Iterate I.
Yeah, we need to bump up I inside of our loop. This is not a for loop, so we need to make sure that we bump up our counting variable. Otherwise, this will get stuck in an infinite loop, and we would hate that. So this should be it. This is all we need to do to figure out the node that is before the node that is the query. So we're going to make very, very sure as we continue this process that we are never passing an index into this that is outside of the purview of the length of the list. Note that we don't need to throw an exception assuming that the user doesn't do this because the user does not have access to this method at all. So we don't have to worry about our, as I will call them, dumb user, because they don't have the ability to mess this up. If this throws an exception, it's our fault. Or if this breaks our program, it's our fault. The user cannot mess this up. So now that we have this find node before, we can start writing the add that is in the middle of the list, because we're going to want to be able to access the previous node. And now, rather than saying .prev as we would in a doubly linked list, we'll just call this method, and that will be the equivalent of saying .prev. So it's not too much more difficult to implement the .prev, but do note that there might be a bit of a time cost for this. We'll talk about that later. We'll probably come back to this when we start talking about efficiency in a lot more detail. I like to keep like functions together. So I wanted to write the second add right below this add rather than having this other random method in between this add and the other add. So we are going to go ahead and implement the other one. So let's go ahead and do that. Since this is part of our interface, we need to override the interface. So we're going to override. It's going to look almost exactly the same as the previous one. So I'm just going to start by copying this line and making associated changes to it. So in addition to the element, and I think according to our interface, we said that the index is going to come before. Note that when you have an interface like this, the exact parameter list must come in the exact order that the interface specifies. If you were to try to implement add where the index came after the element, you would get an error. So always refer back to your interface and make sure that your implementations are following the exact parameter order as your interface. So we need the index to come before. And it threw two exceptions. What was the other kind of exception I said it was going to throw? An illegal argument exception. So we are also going to add an illegal argument exception. All right. How are we going to do this? Is anyone going to give me a basic overview of the logic that we need in order to add in the middle of a list? Now we're passing the index, so we want to insert this element at the associated index that are being passed in as the parameters. How do we do that? Yeah.
We have to iterate to the index that we're trying to add into that, and then either add it to the previous next, or we could just Yeah, previous next.
Yeah, we're gonna need to somehow access that previous node, which is why we wrote this find node before we do this, so that we can access that previous node. But yeah, we'll need to go figure out where that is and then insert it into the correct place in that. As usual, before we get started, if we're gonna throw some exceptions, we should do some checks to make sure, since this is something that the end user can just call, since this is a public method, we want to make sure that the user has passed in parameters that make sense. So we need to write a couple of if statements to check and make sure that the element is not null and that the index is in the appropriate bounds. So let's first do the illegal argument exception. Why not? What would the check look like to make sure that the index is appropriate?
It's above or above -1, I guess, so equals 0.
So we want to identify where the exception would be thrown. So the exception should be thrown if the index is below 0 or above the length of the list. So we want to say if index is less than 0, or if index is greater than, I think we want to call a method we haven't implemented here, size. Note again that even though we haven't implemented this, the IDE says that it's fine. I mentioned why this was last time. Does anyone remember why this is not underlined? Even though it's not implemented?
In the interface.
It is in the interface. So it's looking and saying, all right, the error for this is going to be up in right here. This error says that we haven't implemented the inherited abstract method. And you can see that it even tells you size. It tells us that we need to implement size before we can use this linked list, because it implements the list interface that we wrote. All right, so we want to check, we want to make sure these indices are in bounds, so we're just going to throw a new illegal argument exception. There's too many of them. That one. And we will tell the user that this. All right, how about the null pointer exception? How are we going to check for the null pointer exception? Yeah.
Actually, I just have a question.
Yeah.
about the if statement, so can you still set it up as like I did before, where it's just one line?
Oh, yeah,
Their name?
absolutely I could. So the way to do that would just be to get rid of this, get rid of that, and now we're good. So these are perfect, these are absolutely equivalent to each other. This is just the if statement that is the single line. I do like doing it this way, but I would like to model it both ways. There's no way that is more right or more wrong. This will just be a personal preference for you, whether you prefer one or the other. If you're not doing a single thing that can't be multiple things, like throwing an exception, then it's fine, but I would highly recommend using the curly braces if you ever might choose to go back and add a second line to the if statement. Again, as mentioned last time, it's not great if it'll be a very annoying bug to find if you have two statements inside of the if, because and like syntactically like this, because the code will compile and it will run and it will give you it'll give you a wrong answer. And you won't know why that is without trying to figure out, that'll be a pain to debug. So sure, I'll leave it like this for now, but again, either way is perfectly fine. Great question. Other questions? All right, how do we check for the null pointer exception? Yeah. If the element that is passed in is null, meaning that it does not have an associated value, then we want to throw a new null pointer exception. And tell the user that always include these error messages wherever you can. If this ever gets thrown, having some kind of useful error message for the user is tremendously useful. Having things break nicely is a huge boon for figuring out what went wrong. People will use your code if it is user-friendly. People will not use your code and send you a very angry email if it is not user-friendly. All right, now we have the exceptions out of the way. So now we need to think about how do we actually add in between this. So let's start with the node construction, because we need to make a node object that is going to contain this element in it. How do we do that? I always have the hardest time coming up with names for variables because this is actually a very important decision if something goes wrong in the future to be able to debug. So you can do something like call it new node, but that also isn't particularly useful because it isn't more specific than just it's a node that's being created. So you can do something like added node. We'll use new node for now, but I'm not super happy with it. So remember that a node, if we look back at our node class, the constructor for this takes either just the data or the data and the next. Which one of these constructors do we want to call?
Data and the next.
Do we know what the next is yet?
No.
We do not know what the next is. So if we don't know at the time that we're calling it, then it's something that we eventually have to figure out. Because we need to go figure out what the previous node is so we can query the previous is next to know where we want to insert in the middle. Yeah,
Couldn't you just do like find node before index dot next?
we could.
And then just
We could, but since these are both publicly accessible, we can also set them once we know. So we absolutely have a branching point here where we could do it. We could implement this either way. So if we're doing this without calling find node before yet, then we want to pass it just the element. And that's fine. But do note that we can't query this node's next, because if we go look at the node class, next is null when we use this. So we need to make sure that we set next before we query next. Otherwise, we'll get a no pointer exception. Okay, so we've made the node. Now we want to actually, we have two things that we need to check. We need to make sure, we kind of have a branching point here, don't we? We need to figure out where this is in the list, or rather if the list is empty, or if we're setting it at the beginning of the list or in the middle of the list. So if index is 0, then we don't want to call find node before on the head. So let's actually check if index is 0. Then we want to set, basically if index is 0, let's get a visual of this on there. So we want this to be at the very beginning of the list. So here we have a node that is the current head. And this will point off, it doesn't matter whether this goes to another node or not. But what do we want to do? Where do we want this to end up? What should the end result look like?
And you know this next one and then end the three side.
Yeah, so we want to make this new node that I'm going to be different color. This is going to be new node. And we want it to point to head. So. New nodes next. Should be head. And then we need to also reset the head because now the head isn't the head anymore. We've made a new head. So we want head to be the new node. There's one last thing we need to do in here. What is it?
Reset.
Yes. We added a new node. We've been successful with this, so we should absolutely do that. And I guess we should also, since it's a Boolean, we should return true since we're at the end of our logic. We made the new node, we put it in the appropriate place, we incremented the size, we're done and we're successful, so we should return true. Great. So now we need to consider where we have a slightly different scenario, where we have the new node that we're making. So this is going to be the node that is found by find, what did I call it? Find brief, find last, find node before. I'm just going to call this NB. Find node before, this is now new node. And this is now the, I guess this is going to be the node at the associated index for whatever they passed in as the index. So we're going to call this like the index, the node at that associated index. So the index is going to tell us how far to get here, but we can find this from find node before is next, since this currently points here. So what associated changes do we want to make? I'm going to put those in a different color as well. And I need to refill most of these. I guess I have a full orange, don't I? We'll do this in orange. What needs to change? Here is our current state. What needs to change here in order to correctly insert new node in the middle of find node before and the query index? Yeah.
Usually have to set the find node before to new node, or the find node. The find node before dot next new node.
Yeah.
Don't you wanna do the new node one to the index first, because it'll get a reset on that?
Yes, if we change this, then we have to, how do we access this anymore? We've kind of broken the list. So we need to order these in such a way that we want to do this first and this second. Does that make sense to why that is? If we do this first, then we've broken this arrow. This arrow doesn't exist anymore. And so we have no way to access index anymore. So we need to make sure that we connect to index before we break this. So as always, before I write code, I want to have some kind of little image in front of me to make sure that the code that I'm writing mirrors the image or the idea of what I want to do in my head. It gets very easy to get lost in the logic of code and keeping track of exactly what's happening in the order that you need to think about. So this isn't too bad to draw this out and to think about the associated logic. And then it's much easier to tie this logic back into the code than trying to just use the code. So whenever you're coding, have out some kind of, it can be paint, it can be a sheet of paper, just something to draw on or draw with so that you can draw out the associated logic and make sure that what you're implementing makes sense. All right, so we need some other. If it's not at the first index, then we still have this new node, great. But now we need to, how do we want to start?
So loop to find an index, how do I want to go to?
I actually think that loop is embedded in our find node before. So we can use that method call to not redo the loop process in our code. It's gonna be, from the computer's perspective, it's the same amount of work. We're still calling a loop one way or the other. But as computer scientists, why write two loops when we could write one loop? It's a great idea. It's exactly right, but we've just already done the work. So let's make a node. We're gonna call this prev. We will call find a node before, and we will pass it. We want the associated index, right? This will get us the node that is before the node that is at index index. So that should get us this. So now prev is going to be this. I'm just gonna rename find node before we go into the code as prev, since we actually have a variable name for it now. And this would just be the same as the dot prev of index if we were had a doubly linked list. So now we have the prev, so now we're ready to start doing the logic of manipulating. So we want to do step 1 first. So we will say new node dot next equals, what should I set it as?
Equalness?
Yeah. What next? Pun intended.
Isn't that doing the number 2?
So before we break this, we want to set this pointer, new node dot next. This is right here. We're going to set this to point at what this currently points at. So this orange X isn't here yet. So we're going to say point this where this arrow is pointing, which creates this arrow. Great question. Does that make sense to everybody else? What comes next? How do we do step 2?
Like the previous next.
Great. What's left to do before we're done?
So
Yep, bump up the size. And return true. I think this finishes this off. So this is our add in the middle of the list. I agree that everything inside of this else does what this image does. Any questions about any of the logic that we just did? Right. So next, we want to start thinking about probably our, we have get and remove left. Get's going to be fairly similar to add, except we're not making any changes. So let's just quickly write get. So if we look back at our interface, we can just go grab this line, throw it into our linked list. This should be public. So how do we get an index out of bounds exception from get? Yeah, basically the same idea. once we're done with this. There's one other way we could get this index out of bounds exception. Can anyone think of or see when we also might get an index out of bounds exception beyond just index is less than 0 or index is greater than size? If the list is empty, yes. So before we even query less than 0, it doesn't really matter the orders. We'll say if the list is empty, then great. How do we proceed? So we passed in an index. We want to grab the value at index. Are there any special cases that we need to consider? In general, we're probably just going to want to call find node before and you reuse that code and reuse that loop. Are there any cases where this list you might not want to call find node before?
You're getting the first element.
Yeah, if we're getting the first element or if the size is 1, which I guess is the same thing. So we can do that. One nice thing about storing this field current that we have up here is it's always going to be the last node in the linked list. So we can bypass some time of calculating the find node before. If we add one extra line of code, we say the index is the size minus 1, then we can just straight up return all right, now I think we've exhausted the cases where we can save some time. We've exhausted the side cases. So now we just have our generic case left. So we can just make the node. So we find the node before, and then we want to grab its next and return its data. Right, so we have the node before the query node, so we want to go from the query node, the node before the query node to the next to get to the query node, dot data to return the data. So we can return per dot next dot data. Java is the language of lots of dots. You'll find yourself doing a method call dot another method call dot another method call dot some field, something like that. So just get used to it, it's pain. One of the things to hate about Java. But I think this does get. Anyone see any issues with get? Yeah,
I didn't use override.
I should have overridden this. You're absolutely right. Good call. We're gonna do the same thing to remove before I forget. All right, so it is time for us to consider removing. So removing is gonna be probably a little bit, it's about the same difficulty as the second ad that we wrote. So we're gonna wanna draw out an image for this before we do this or get too deep into it. I will grab the first remove that we're going to implement and throw that in. Since this is something we want the user to be able to do, we're gonna make it public. And now we're going to talk about the details. So we are ready to actually implement it. So we write our curly braces. What's gonna cause the index out of bounds exception? It's exactly like the get. Actually, I'm gonna make this a little easier, so. I already hate copying and pasting. Remember what I mentioned, that if you're copying and pasting, this is a bad idea. I'll leave this for now, since this is the only couple times we're gonna do this, but I'm already starting to think, maybe I should factor my error checking out into its own method. So that I don't have repeated code. If you find yourself doing the same type of error checking at the start of each method, factor it out into a new method. It'll save yourself a lot of time. It'll be useful. All right, if we're removing, we again have the same two cases as we did for the adding. So I'm just gonna scroll right back up to the add. We had two cases where if we were adding at the very first element in the list, and if we were at the somewhere in the middle of the list. So let's think about those same two cases again. So we're either going to be removing that head of the list. So we have. We don't really know if this points to another node or not. We just know that it's a pointer to somewhere. Could be null, could be another node. So we're going to say if index is 0. How do we deal with this case? We want to remove the head. It's data first, because remember that remove returns this generic element. So before we get rid of this node, we want to make sure that we store it off. Absolutely. No falling. All this, I guess, data. And once we are done with this, we're going to return it. Great. What's next? I would argue that it doesn't really matter what's here. It doesn't matter if there's a node here or if this is a null pointer. We can catch both of those cases with a single line. What is that line? That would be the case if this was a null pointer. What if there's a node here? Yeah. If head.next is null, this will set head to null. If head.next points at another node, it will set head to that. Now note that we don't have to do anything else to head. Have we heard of the concept of garbage collection before, or know what Java's garbage collector does? So this is a program that runs at a very low level during any program's execution. If at any point there is no reference to an existing piece of memory, it will go free that memory. And note that I write this like this, but what's really happening underneath the hood in memory is we have this variable, this field that we call head, and it points at this node. So there exists a reference in memory to this node. When we say head equals head dot next, what we're doing is we're changing this arrow to point here and getting rid of this arrow. Which means that nowhere in memory is there a reference to this node. So the garbage collector just comes and frees that for us. We don't have to specify that that's going to happen, it just happens. And this is what prevents a memory leak. If you've ever run something like a game and just slowly noticed over time, it starts taking more and more and more and more memory until your computer starts acting really slow or the program crashes, something like that. Those are called memory leaks and they're a pain. They're very difficult to do in Java because of that garbage collection. So it's something that is just being done for you underneath the hood. The issue with it is that's a program that's running at the same time, so it makes whatever your program is doing slower. So as always, there is a trade-off, but that's what that head equals head dot next is going to do for us. Handles both cases very nicely. This should successfully delete the node, so we should change the size. And we should return our value. We stored that off into something called data. What if we're deleting in the middle of the list? So now we're going to have this node that we're again going to call prev, but it's really found from find node before. We're going to have the node that we want to delete. And we have the node after the node that we want to delete. So prev will point to what I'm calling evil because we want to make it go away. And evil next points off to something. This could be null. It could be the end of the list. So we actually don't know if this is here or not. How do we want to handle it? So yeah, go ahead.
Just sort of data that's in the node you're trying to remove.
Yeah, so since we're doing this 2 times, I'm actually going to pull this. Values, we want to find the node before and store up its data. It's not quite the same as before. If it was the same line between the if and the else, we just want to factor it out before the if. Why do something twice when we can do it once? So we're going to say that we want to store the node. And after we do exactly that, we want to store off its value. Actually, it's, yeah, we want prev.next.data, don't we? We're unfortunately out of time, so we're gonna have to come back to this, I think, tomorrow. But we should be able to finish this off tomorrow. And we should also be able to start talking about iterators, which will be very useful. They are super useful for any time we have a collection, and it would be great to be able to start talking about it and actually implement it in this linked list, as well as fully test it and see it working in action. But I will see you tomorrow for that.
Hi, Chris, I have a question.